Happy morning all. In this lecture we are going to see derivations of Maxwell's equations based on law of electricity and magnetism. So before going to Maxwell's equation, we'll just recollect two laws which will be used in this derivations. First one, Gauss divergence theorem. In Gauss divergence theorem, it tells that you can convert a volume integral into a surface integral. That means if you have a vector, if you take volume integral of that, integration of del dot A, which is over a bounded volume, will be converted into a surface integral. So this is A vector dot ds. So using this theorem, you can convert a surface integral into volume integral and volume integral into surface integral. So this is Gauss divergence theorem. Next, Stokes theorem. So using Stokes theorem, we can convert surface integral. We put del cross A. If A is a vector, so del cross A, which is a surface integral, a closed surface integral, will be equal to a line integral of that vector A dot dl. These two theorems, which converts one to the other one. Okay, so Gauss divergence theorem converts volume integral to surface integral, and Stokes theorem converts surface integral to line integral, and vice versa. Okay, so now before going to the Maxwell's equation, deriving the Maxwell equation, it is always better to draw a tabular column so that you won't forget the final result. So the tabular column, which gives you a clear idea, okay, what we are going to derive and what we have to attain, everything. So for this, so let us Maxwell's equation, he converted into two forms. First one, differential form. The other one, integral form. So first law, he derived from basic Gauss law of electrostatics. So from this, the differential form is del dot d equal to rho. And the integral form of the same equation, so it is a del dot ds equal to volume integral del dot rho dv. Okay. Second equation, he derived from Gauss law of magnetostatics. In this, del dot b equal to 0, and integral form of this equation, integral b dot ds equal to 0. And third law from Faraday's law. Remember this, sometimes they will ask the question directly, okay, derive Maxwell's equations from electrostatics, Maxwell's equation from magnetostatics, like that, instead of mentioning first equation, second equation, like that. So remember which equation is derived from which basics law. Okay, so the third equation from Faraday's law. From Faraday's law, we derived del cross E equal to minus dou B by dou T. The integral form of this integration of E dot dl equal to line integral, surface integral dou p by dou t into ds. And so the final fourth equation derived from Ampere's law. So from this law, del cross H is sigma E plus dou d by dou t. And integral form of this line integral of H dot dl equal to the surface integral of sigma E plus dou d by dou t into ds. So make this tabular column so that you will get a clear idea. Okay, so what we are going to derive, from where we have to start and where we have to end. Okay, so now we'll go one by one. Maxwell's first equation. So we'll start from basic law of electrostatic Gauss law. We know that according to Gauss law, the flux flowing out of a surface is E dot ds, which is also equal to Q by epsilon naught. For this, let us consider there is a volume in which the total charge is Q, so that we can write, and the surface charge, volume charge density is rho, and total charge is Q, so that I can write like this: the total charge is integral of rho into dV. So let it be equation 1 and equation 2. Now apply equation 2 in equation 1, so that I can write like this: integral of E dot ds equal to 1 by epsilon naught. Instead of Q, you write this second equation: volume integral rho dV. Now bring this epsilon naught this side, so that integral of epsilon naught E into ds equal to volume integral rho dV. Equation 3. Now, so d, displacement vector, is epsilon naught E. Substitute here. So integral d dot ds equal to volume integral rho dV. If you see here, this is the first equation, Maxwell's first equation in integral form. Okay. So in integral form. From this we can continue and derive in differential form. So now if you see here, this side, left hand side is surface integral, and right hand side it is volume integral. Now I want to convert both the sides into any one of the integral. So what we'll do, we'll just convert this surface integral into a volume integral by applying Gauss divergence theorem. So based on Gauss divergence theorem, as we told earlier, if you convert, okay, so if you apply Gauss divergence theorem, this surface integral d dot ds will become volume integral. So del dot d into d. So apply here. So convert that left hand side of our equation. So we'll mark this equation 4. Okay, so if you apply here, we'll get like volume integral del dot d dv equal to volume integral dv. If you see both the sides, we have volume integral and it will be equal for all possible limits. Okay, so that the equation, okay, so we can cancel the volume integral del dot d equal to rho. So if you see, this is the first equation in differential form. Now we will derive Maxwell's second equation, derived from Gauss law of magnetostatics. Okay, so here we will start deriving the second equation from Biot-Savart law. We know the differential form of a Biot-Savart law, dB mu naught by 4 pi ideal, a current element, sine theta by r square. Now the same can be written in a form of vector notation. So dB vector equal to mu naught by 4 pi ideal vector cross r cap by r square. So for this second equation, let it be 1, this is 2. Integrate on both sides to get the complete magnetic induction. So if you integrate, you will get d vector equal to mu naught by 4 pi, and we can take this r square out. So 1 by r square integration over ideal r cap. Okay. Now let it be equation 3. We know that the current density J equal to I into A, because J equal to I by A and I equal to J into A. Sorry guys. Multiply both the sides with dl. So dl J into A into dl, where A is the area, dl is the length. If you multiply with the area by length, you will get a volume. So IDL equal to J dot dV. Since the length is variable, so if you multiply, you will get a volume, a variable volume. Now instead of IDL, we can put J dV. So in this equation 3, okay, so instead of IDL, we can put J dV. So the equation now becomes B vector equal to mu naught by 4 pi by r square integration over, instead of ideal we are putting J dV. So it will becomes J cross r cap into dV. Now take del on both sides. Okay, so divergence del dot B vector equal to mu naught by 4 pi 1 by r square integration del dot J cross r cap into dV. That will be equation 3. Now, so if you expand this, okay, you will get del dot j. Okay, we know that del dot j equal to 0, where taking a dot product with a vector will use a divergence. Okay, so since the j is a constant, if you take a divergence, you get a 0. The entire right hand side of the equation 3 will become 0. So del dot b equal to 0. You see, this is the integral form of second equation. Now, just see here, it tells that universally the magnetic monopole does not exist. What is del dot b equal to 0 means? If we take any surface, okay, if we take any surface, the magnetic flux entering will be equal to the flux which is leaving. Okay, or we can put it in a better way. Let us take a volume. Okay. If you keep, just consider a North Pole, okay, inside this volume. So if the lines which is coming out, okay, so 10 lines are coming out. Obviously, we know that their magnetic field lines are closed loops, so they will come on the other side. Okay, so you cannot keep a North Pole inside. Okay, obviously the South Pole will exist. Okay, so monopole does not exist. This is what this expression implies for us. Now, if we take over a volume, okay, so let us take over a volume. So over a volume, this divergence is equal to 0. So in this volume, this del dot B equal to 0. Okay, in this volume, as I told, let us take a volume. Okay, B. In this, the flux which is coming out through a surface will be and enters on the other side. Okay, now using Gauss divergence theorem, we can convert this volume integral into a surface integral. So if you apply Gauss divergence theorem, okay, this equation will becomes B dot ds equal to 0 over a closed loop. So this is Maxwell's second equation in integral form. We will continue with Maxwell's third equation, which is derived from Faraday's law of electromagnetic induction. Okay, so according to Faraday's law of electromagnetic induction, the EMF induced will be equal to the flux linked with the coil. Okay, so the rate of change of flux linked with the coil. So this is Faraday's electromagnetic induction law, and we know that work done, okay, when we are moving a charge, so the work done, okay, will be equal to E dot dl, where E is the electric force and dl is displacement. So work done, force into displacement, okay, over a line. So now if you compare these two things, the work done, the EMF will be, so E dot dl equal to minus d phi by dt. Okay, so for this is the equation 1, 2 and 3. Now the magnetic flux phi in magnetostatics. Okay, so we are going to get this flux of magnetic induction. We can write like this. So the magnetic induction B, okay, in the relation between these two things, we can write. So flux is equal to V dot ds over a surface. Okay, now in a surface, okay, the flux which is coming out will be equal to V dot ds. Now equation 3 will apply for phi. So E dot dl equal to minus d by dt surface integral V dot ds. Take this differential term inside, so minus integration of dB by dt into ds. I can rewrite the expression like this. E dot dl, this is a line integral, minus surface integral of dB by dt into ds. If you see, this is the Maxwell's third equation in integral form. Okay. Now, the left hand side is in line integral and the right hand side is in surface integral. Convert this. Okay, left hand side, by applying Stokes theorem, we can convert line integral into surface integral. So by applying Stokes theorem, if you apply left hand side, so your line integral of E dl will become a surface integral, okay, as del cross E into ds. So substitute this, okay, equation 4, 5. So left hand side, substitute this 4, you will get surface integral of del cross E ds equal to surface integral minus dV by dt into ds. Okay. Now, if you see both the sides, we have surface integral. So now this will be valid for all possible limits So we can cancel the surface integral. Finally, we'll get del cross E equal to minus dB by dt. Okay, so which is the differential form of Maxwell equation. We will continue with the Maxwell's fourth equation. Maxwell's fourth equation is derived from Ampere's law. So according to Ampere's law, so the induction over a closed loop, okay, will be equal to mu naught times the current enclosed by the loop. Okay. Now, instead of V, we know that, okay, so we can write mu naught H, okay, magnetic intensity. So we'll substitute here. Let it be equation 1. And we know that I, current, equal to J dot ds over a surface. So substitute left hand side instead of B, mu naught H, and right hand side instead of I, substitute surface integral J dot ds. Now the equation 1 will become like this. So a line integral mu naught H into dl equal to mu naught, instead of I, a surface integral J dot ds. In this, we can cancel mu naught. finally we'll get a line integral of h dl equal to a surface integral of j dot ds. Now J is the current density. The total current density, okay, is given by a conduction current plus a displacement current. Hope we have derived this. Okay, so that the total current density equal to conduction current plus displacement current. Let us substitute this in equation 3. So we will get like this. So a closed line integral h dot dl is equal to surface integral. Instead of j, we can put sigma e plus dou d by dou t into ds. So if you see, this is the integral form of Maxwell's fourth equation. Now, very simple thing, we have to convert this into differential form. If you see here, left hand side we have line integral, right hand side surface integral. So, applying Stokes' theorem, you can convert this left hand side into a surface integral. So, if you apply Stokes' theorem, okay, so the line integral h dl will become a surface integral del cross h over a surface. Substitute this in left hand side. So what will get? So surface integral del cross h equal surface integral sigma e plus dou d by dou t into ds. Now if you see this equation, both the sides we have a surface integral, so this will be equal for all the limits, so we can remove the surface integral. Finally we will get del cross h equal to sigma e plus dou d by dou t, which is nothing but differential form of Maxwell's fourth equation. So by this we derive all four equations in both differential and integral form. Thank you.